All right. So, walking through these common mistakes on this first quiz. What is negative 2 cubed? Negative 8, which means the cube root of negative 8 is going to be what? Negative 2. So we can have odd roots of negative numbers because negative 2 when cubed is in fact negative 8. We can do that. The ones that we can't have negative roots of are positive or even indexes. Like I can't do the square root of negative 8. I could not do a fourth root of negative 8. That's when we get our imaginaries. When we have even root or even indexes of negative numbers. Odd indexes, we can do whatever the heck we want with because they can be all over the place. So we're not going to get I when it's an odd power or an odd index. I is only for the evens. So then let's look at this one here. 2 to the power of negative 3. What does that do? What does the negative in the exponent do? Flips it, turns it into a fraction. This becomes 1 over 2 cubed. Which means it's really 1 over 8. It takes that 2 cubed and moves it to the denominator. It does not make the whole expression change. It's just the 2 that's moving, but that's the only piece we have here. So make sure we're being careful with things. I had a lot of people give me things like negative 6, where we multiplied things together in interesting choice of ways. So I feel like a lot of the mistakes that were made on this first quiz were made out of speed, rushing, and not reading carefully, and running with our first instinct and not looking back. Like we had an idea, we ran with it, and moved out of our lives. Slow down, look at what we need to do, and if you've got time, go back and look it over again. This next one, I had a lot of people miss something really, really, really small on this. There was one like this. What happens to negative numbers when we square them? They become positive. Please do not tell me that negative 3x cubed is going to be negative 9. There are a few ways to think through this. If this is one that you did struggle with, you can either break it into pieces and do power over power. You could make this be negative 1, positive 3, x cubed, and square all the pieces. You can write it out, negative 3x cubed times negative 3x cubed. Many different strategies through it. The one that I feel is most intuitive is to take this as negative 3 to the first squared and x to the third squared. That feels a lot more exponent rules that we've been through, familiar. Because negative 3 to the first power squared should give us what? What is negative 3 squared?
9.
Positive 9. Negative 3 squared is positive 9. What is x cubed squared? X to the 6. Powers over powers multiply. That is x to the third times x to the third. So we should wind up with x to the 6th. If it is a power over a power, you multiply them. If we are multiplying the bases, that's when we add. I had a lot of people adding when we needed to multiply. All right, this last one we're going to do in a couple of places, and we're just going to get it into notation. We're not going to fully simplify because I wrote this on Saturday and didn't work it through, and it winds up super gross. But it gives us the vibe of the things we need to talk about. Because when we have something like this, it is always a good idea to start with, there's a lot of stuff happening. Order of operations says simplify in the parentheses first. So simplify first. I had a lot of people on the one, like there was a big fraction that had this. Y'all just like started throwing in cube roots places. I'm like, simplify. Make your life easier. Simplify. What's inside? What can I do with what's inside my parentheses here? The 2 and 4 to make a 1/2. So my 2 and my 4 are going to simplify down to be, there's a 2 on the bottom. There's a 1 in the numerator, which you don't have to write, but we can. I was going to say, my x squared, I can't really do anything with it, but that x to the minus 2, what's happening to that? It goes up to the top. It does not make the whole fraction flip. Just the x to the minus 2. Just this guy changes sides. He goes across the fraction side. I had at least a few people take the whole thing and flip it on its head. It's just that guy that moves. So we're going to have our 2/3 is still just hanging out here. Okay? I still have things to simplify inside my parentheses. What can I do inside my parentheses here? Add my exponents on the x's. We're multiplying the bases, so I'm adding my x squared and my x squared, so 2 plus 2.
Why did you keep the 1 for the 1/2?
You absolutely can, but 1 times x squared is the same thing as x squared.
Okay.
If it helps your brain, put the 1. Totally fine. It is absolutely not wrong. It means the exact same thing. So you can either put 1x to the 4th, or you can just put x to the 4th over 2. Simplify before we try and do funky weird things. Make your life easier. Because now we have this fractional exponent. And it's gross. What is the 2? Is the 2 the power or the index? Power or index for the 2 on the exponent. This 2. Is, well, just power or index, the 2? Is it your exponent or is it in the root?
Exponent.
It's your exponent. That is our power. The 3, is that power or index? Index. This is the piece that goes into the root. So it's the cube root, and this is squared. Just putting words on here. And I'm off the edge of the screen, and I don't feel like making it bigger to the right. Squared. So it's taking this piece squared and doing the cube root. So again, we have a couple of options for order to go through. You could do our cube root of x to the 4th over 2, and then, blue pen, thank you, square it. Or we could do our cube root of this whole thing, the x to the 4th over 2 squared. Either way is fine. One may be slightly easier than the other. In this particular case, looking at the left, the blue with the cube root of x to the 4th, that's not going to be super pretty because it's going to have some things in, some things out, like a whole lot of mess. Cube root of 2 is also not something I know. So if it's not something we can do easily, probably the exponent side is going to be better. The only times really it's going to make sense to do the cubes first, or the roots first, is if it's simple, or if you've got big numbers. If we got big numbers, we probably want to make them smaller before we make them bigger again. If you make them even bigger, it's going to take even longer to simplify. So I'm going to do it purple way. We're going to have our cube root, and just so we can practice our powers over powers again, what is my numerator going to be? X to the what? 8th. And our denominator is going to be what? 4. 2 squared. We have to square both pieces. And for us, we're going to stop right here, because here's where I looked at it and went, oh, ew. Because we can't take cube root tidily of any of these, and like, the point was not for us to get further into rationalization stuff, it was just go through mistakes. It's called I wrote it on Saturday and didn't do it, and it was a Saturday. So we're going to stop right here. But that got us through the mistakes that people made. We either flip-flopped which one was the power, which one was the root, or we made some interesting simplification choices, or we made some mistakes on simplification. But I felt like looking through it, it felt like a lot of the mistakes that were made. When we slowed down on the hard problems, we did better than on the really short ones where we were just trying to fly through them. So hit the brakes, take your time, slow down. You don't have to be first. Don't have being the first one done be your goal. Okay, slow down, use your time. If you're not sure what question's being asked, ask me. I can always clarify what's being asked. Okay? I had a lot of people get caught up in the absolute value with our little restriction, the little if x is less than or if x is greater than. A lot of people got caught in that and weren't sure what we were doing. So there were a lot of little mistakes. So we're gonna move on. Moving on from that. Luckily, that first quiz, if you looked at your grades before and after, they weren't like throw you in the garbage can low. Like, it didn't pull us all the way down. But for most people. Also, I sent a message out to your grown-ups, and I do believe I included students on it as well. This first couple of weeks especially, until we get to our chapter test on September the 6th, grades are volatile, super volatile. Until we get a chapter test in there that takes up that biggest chunk, things will shift wildly. So give yourselves some grace, some patience. Take a deep breath. The first quiz is not intended to scare you, but I know so oftentimes it does because it's a big step in difficulty and in speed and in how the questions are asked and things like that. Okay, so those of you who got a little extra nervous on that first quiz, I can get you there. I can get us where we want to be. And at the end of the semester, whatever our worst quiz is, drops. Like, it just straight up won't count. Okay? So, all things aside, let's move on and look ahead at the next thing. Okay? So we're going to be dealing with fractional expressions for the rest of this week, basically. And all a fractional expression is a quotient of two algebraic expressions. It just means it's fractions. We're going to be specifically in our rational expressions, which is when we have two polynomials. We talked about polynomials a lot last week. And there's a little example over here of a rational expression. This is a rational expression. I have a polynomial on the top and a polynomial on the bottom. They're both binomials. We're also going to talk about domain, which means we need to remember what the heck the domain is. What is the domain when we're talking about anything mathy? Our x values. So the domain is the x values, or the whatever our input. Usually x value is what we substitute in, so I will often put it as our input because sometimes the book uses different letters and we still can put it in there. The x values that work. It's the x values that work. It's the things we can substitute in and get an answer. It might not be pretty, but it's an answer. In rational expressions and rational functions, we are going to have something called a domain restriction, which we have already actually seen this year. That was when our absolute values thing with the x has to be greater than 3 or y has to be less than 7, whatever those are. That's a domain restriction. And what it is it's a rule that is stated that puts a limitation on your domain. So a domain restriction is a rule that is stated to make sure and I'm in the middle of a sentence here, but I'm going to stop for a second. Because we're dealing with fractions and an expression, and fractions have some special rules, right? What is the one thing we can never, ever, ever have in a fraction? We can have negatives. think about in our denominator. What's the one thing that can never be in the denominator? 0. So there's a limitation on what x's I can substitute in because I can never have a denominator of 0. We can't divide by 0. So we need to make sure our denominator is never 0. Because that gives us a problem. It is when we get in the if you did it in a calculator, it would say domain error or system error. If we were substituting things in, like the robot brains explode, all that kind of jazz. If you think back to when we graphed these in Algebra 2, that would be where we had the hole, the removable discontinuity. We'd stab a hole in the picture. So it would poke a hole in it. So we can't get rid of them because it changes something about our function. So, for example, just looking at this piece here, we're not going to try and simplify or anything else like that. We're just going to figure out the domain restriction for our example function over here. What value of x would cause my denominator to be 0? -3. If x is -3, my denominator is 0, and that's a problem. So the way we state our domain restriction is we'll say that x cannot equal whatever that value is. So x cannot be -3 for this particular case. And when it comes time to graph these, we will need to have those values, which we're going to get into before the end of this chapter. In fact, I think we get to it next week. 2 weeks. So we will be graphing these eventually. So we need to make sure we can identify those domain restrictions. Okay, because it changes what x values we can use. It changes where asymptotes may be. It changes where discontinuities may be. And we're going to practice a bunch of times starting with our simplifying. Okay, so we're starting out fairly simple. We are going to find our domain restrictions for almost all of them today. And the one that we don't, I will tell you why, because I don't want to deal with it. So we're going to start with simplifying. And we're in fractions. We got some polynomials. When we are simplifying fractions and simplifying pieces like this, we can only simplify things that are multiplied together. I cannot take things that are being added or subtracted. So before I can do any simplifying at all, it has to be in factored form. Has to be, has to be, has to be. We cannot simplify when there's addition or subtraction in our denominator without factoring. So looking at this first one here, the way I think about it when factoring is I'll do my numerator, I'll do my denominator, and then see where they meet. Just try and work one at a time. So looking at this piece here and looking at my numerator, what can I do to factor this numerator? Yeah, it's got a GCF of 2. So I'm going to write this as 2 times what? What gets left over? X plus 3. Same vibe with the denominator. I'm going to look at my denominator here and say, what is my GCF? 4. When I remove my GCF of 4, what do we have left over? X minus 3. Okay, that was just factoring so far. Now that I've factored both top and bottom, I can look and see what we can simplify. What can we simplify here? The 2 and the 4. Because both are divisible by 2, which means when they simplify, what are we going to wind up with? 1 over 2. So that's going to simplify down to a 2. They both divide by 2. So I'm going to rewrite how I did that on with that. So this becomes a 1, that becomes a 2. There. I feel like that's clear. Does anything else simplify?
Well, second, because you're. That's a trick question.
No, it does not simplify. No, it doesn't. Trust yourselves. I was like, I saw a lot of you have that instinct of, why'd she ask the question if it was a no? I will often ask questions, even if there's not anything we can do. Because, again, on the homework, on quizzes, I'm not there to say, all right, so let's go to our next step. You have to be able to tell there's nothing else to do here. So our finished answer is going to be our 1 times x plus 3 So just x plus 3. We don't have to have the one on the outside, and we don't have to have the parentheses on it if it doesn't have anything multiplied outside. In our denominator, we've got our 2 times x minus 3. And I'm 100% okay with that being exactly how we write the answer. When we are simplifying, you do not have to re-multiply it out. In fact, I would prefer that you didn't. Partly because that's how I can tell if you cheated or not. Because if you multiply it out, I know you photomathed it. Because they always multiply it back out. So the last piece I want to do up here is I want us to practice that domain restriction a little bit. So what value of x would give me a problem here? 3. If x is 3, my denominator is 0, which gives me a problem. It can be anything else. It could be 2.9, it could be 3.1, it could be 27, it could be 3.0000001. It could be totally fine. It'd be gross, but we could do it. Oh, I do that a lot. So our x cannot be 3. It can be anything else in the entire existence of real numbers. It cannot be 3, or we have a problem. Okay? Questions on the first one? Cool. Same vibe on the next one. I'm going to zoom it in because I know the teal is awful to read the black on. That is not the button I meant. I did eventually figure out when I was making these presentations to stop putting black text on the teal, but I think it doesn't happen again until next week. All right, so here's our next one. X squared minus 5x plus 6 over x squared plus 2x minus 15. So, quadratic trinomials. We can only simplify when it's in factored form. So, what we need to do is factor it. Yep. So, I'm going to take my numerator. And I'm going to do my x. A times c. 1 times 6 is 6. B is negative 5. What is a pair of numbers? Multiplies to make 6, adds to make negative 5. Negative 2 and negative 3. Since my a value is 1, I don't have to do any more work than that. We can take our little shortcut where we have x minus 2 and x minus 3. When our a value is 1, we do not have to do anything else to factor. I would count that as fully factored, showing all the work. That is plenty. That is all we need to have for it. If you want to do more, if you want to factor by grouping, if you want to throw it through the box, whatever you need to do, absolutely fine. This I would count as the minimal amount of work for factoring that top one. Show me how you got your numbers. Then we're going to do very similar for our denominator. Just need to change colors. There we go. Let's take those red. Yeah, that shows up decently. So similar vibe for our denominator here. A times c is negative 15. B is 2. What is our pair of numbers that multiplies to make negative 15 and adds to make positive 2? Negative 3 and positive 5. So our factored form is x minus 3, x plus 5. Again, I count that 100% as showing all the work we need to for it. That is all we need to have to simplify this. What? I'm not done yet, but that is factored. I'm not done yet. Because what do we notice now?
X minus 3, x minus 3.
The x minus 3's match. So what can we do with them? Cancel them out. Boop, boop. So we're left with x minus 2 over x plus 5. Does that simplify any further? No. So questions on the simplifying part. Because next we're going to talk domain restriction. So we can try that again. Trying to make it so that that doesn't bite us in the butt later on. What value or values cause us problems in the denominator? Negative 5 does. How about for our original equation, which is what the question was about? Is there another value that will cause us problems in the denominator? Because we asked about this. This is this part, right? In factored form. This still causes us problems. So this also is a part of our domain restriction. So just because it canceled out means it doesn't shift our graph all that much, but this will be where we have that removable discontinuity, the holes. When we stab it through the graph, those of you that had me physically stabbed a hole in the picture. They still cause a problem with our domain restriction. So x cannot equal -5 and x cannot equal what? What would cause our problem in the other factor? 3.
So we can get our second answer from the factor form and then
Yes.
from the simplified form.
Yes. So it's going to be, our domain restrictions are going to come from any piece in the denominator from your original question, whether you get it from factored form or from some other method. Factored form is by far your easiest option. So you're going to get it from your factored form. But anything that's in the denominator causes us problems somewhere. Because denominators are problems. In many senses of the word. Okay? And we're going to practice with that. Domain restrictions isn't going to be like a super duper important thing until we get to the graphing part. And in that case, it's a very important part. So that's why we're practicing with it on some of the simpler ones. So when we get to the hard ones, it's not as awful. Okay? So we're going to look at some more. And I know they're super pretty. Here's the next one. I think this is probably the grossest one today, is this one. Okay? So we've got our 2x plus 4 minus x cubed minus 2x squared as our numerator. And x squared plus 5x plus 6 as our denominator. And on these kinds of problems, we'll be given the instruction of simplify. Possibly and include your domain restriction. So when we're looking to simplify, that means first step is to factor everything. As much as we can, every place we can, factor everything. So looking at this numerator, we look at it and we go, that's icky. It's icky. It is. If you want to switch things around so we're in standard form, you can. That's fine. I'm going to work with it as it is because I know once we get it written down, we often look at it and go, I don't want to rewrite all that again just to change their order. It's fine. We can work it in this order. Since we have a cube here, an x cubed, that's my biggest degree. It's also not a difference of cubes because it's 4 pieces. So for the most part, you're going to want to go factoring by grouping or box. I know I've got a couple of box stands. Absolutely fine. Box it up. Be ready to rock and roll. I'm going to do this one factoring by grouping. Meaning I'm going to break this into pairs like this. And I always have it be a plus. So it's plus negative x cubed. I just put that in there to remind me that that's an addition piece right there. I'm going to make a pit stop over here before I get to my simplified fraction. So I'm going to put my my factored form fraction here. So I'm going to go to the right so we can do our removal of our GCFs. Looking at this first pair, 2x plus 4, what do they have in common? 2. So they've got a GCF of 2 with a remainder of what? X plus 2. Looking at my next pair of pieces there, I've got my minus x cubed minus 2x squared. What do they have in common? Minus x squared. With a leftover bit of x plus 2. Right? See where those pieces come from? Because I know the factoring by grouping is still a little bit foreign. Okay, so now I take my x plus 2 and I pull that out like a big old GCF. So that x plus 2 comes out to the front, and that's my first factor. X plus 2. Pulling that out like a GCF leaves me with the leftover bits of 2 minus x squared. The factoring by grouping feels like wearing shoes on the wrong feet until you get the hang of it. It does. It feels awkward. It feels weird. Feels like something's wrong. It's very similar to shoes on the wrong feet. You can get there, but it's not comfortable. So it just takes practice to get there. The denominator, who'd ever thought that a quadratic trinomial, we'd look at it and go, oh, okay, we can do that. Who'd have thought that'd be our happy place or our comfort zone? Because this is just a normal x squared regular quadratic trinomial. A lot easier. Because that's just our x. We even have an a value of 1, so we don't need to do any extra work. Our a times c is 6. Our b is 5. What is our pair of numbers that multiplies to make 6 and adds to make 5? 2 and 3. So our fully factored form of our denominator is x plus 2, x plus 3. Questions on the factoring part of this? Because that's important. It's an old skill, but it's a very important skill. And so 100% I get it. If it's shoved in the deep, deep storage, we're trying to blow the dust off and things get scrambled. So if we have questions, if you have a question, I guarantee you someone else in the room has it too. One, he's got to be brave. Okay? So let's look at this thing now. We're in our simplified factored form thingy. What do we notice? What can simplify? The x plus 2's. Those guys cancel out. So now I have my 2 minus x squared over my x plus 3. Is there anything else I can do to simplify this? Not without making something real, real ugly. Because, I mean, technically, 2 minus x squared, we could try and do a difference of squares with it. It's going to be a hot mess. But we could factor that, but we're not going to. Okay? At this point, we're still working with integers and nice numbers. So this will be our simplified version. We do not have to have the parentheses on it. It's absolutely fine to have the parentheses on it. I genuinely do not care. If it has some sort of GCF, putting this up here, it's not part of the answer. If it had a GCF, then you do need to have your parentheses. If it doesn't have a GCF, you don't. Fine with me either way. Let's look at our domain restriction. What are the value or values that x cannot be for this function? -2 or -3. It cannot be any of the pieces in the denominator. Okay? I think that's the hardest one of the day. Okay? We're going to do the one on the right. We are not doing a domain restriction on it, and I'll tell you why when we get to the end. But we're not going to do the domain restriction on this one. Just telling you in advance. Because it's not pretty. And it's more work than we need to do right now. So we look at this and we're like, ooh, binomials, we like that. It's a little bit more complicated than GCFs though. Because what do we notice? Difference of squares, our numerator. We kind of like that one. Difference of squares, I'm just going to call that DOS because I am lazy. Which means we don't even have to write anything down other than the factored form. What is my factored form of y squared minus 9? Y minus 3, y plus 3. That is all the work we need for that. We don't have to put anything for that. I expect us to know the difference of squares pattern. If we don't know it, you can write it out. You can absolutely write more, but it will save you a bunch of time if we notice that. Then we're going to look at our denominator. What do we see there? Cubes. Yeah, it uses that same formula as the difference of cubes, but it is actually a sum of cubes. Sum, and I'm just going to call it cube. Sum cubes. It is the sum of cubes. What's up? We can do that. It is the sum or difference of cubes. You cannot do the sum of squares, but cubes we can. It's the same formula. That's when we use our SOAP. Okay, so it's that same opposite, always positive. That's the only difference between a sum or a difference of cubes.
Wait, so when you said you have to do soap for that,
Mm-hmm.
so you can't do y plus 3y plus 3y minus 3?
Not quite. You got-
Y
it's-
minus 3y.
It's not, you can't go that far. No. It's that special pattern we talked about on Friday. So let's go through it. Because I was like, you have half of it right, but you kind of like went a little advanced on it. We take what was cubed to make each of these pieces. So what is cubed to make y cubed? Y. What is cubed to make 27? 3. With our soap, that's when we start with our same sign. So this first factor is going to have a plus. Then we take our first piece squared. So we're going to have our y squared. Then we have our opposite sign. So we get our minus. Front times the back. So y times our 3. 3y. And then our last one is always positive. So we're going to put plus. And then like how we started with y squared, we end with our back term squared. So our 3 squared, which is 9. So our sum of cubes, our sum and difference of cubes, it follows that exact same pattern. It's just where we put the operations. What's up?
And soap is only for sum of cubes.
Sum or difference of cubes. That's how we tell the difference. Because if it was difference, so I'm just going to do a theoretical here. If this was y cubed minus 27, it would be the same pieces. It would just be the same sign. And then it would be the opposite sign, always positive. So this would be if it was y cubed minus 27.
Okay.
Okay? Literally the only difference is the signs. Okay.
So where did you get the y squared from?
The y squared comes from this first piece being squared here. Okay. It's from the formula. We did it on Friday. So what I wrote in the black down here, this is just our theoretical talking through the difference between the sum and the difference. Okay? I just don't want us to be confused by that here.
I don't have it completely memorized.
Understood? It'll show up in our practice as we're going, especially through these rationals. It shows up several times in there. So we'll get more practice with it. So what do we notice here? Going back to our original problem.
You can cancel out the y plus 3.
The y plus 3's cancel out. So we're left with our simplified version of y minus 3 over y squared minus 3y plus 9.
So why can't you do domain restriction for the y plus 3?
We could do domain restrictions for this. Absolutely we could. But y squared minus 3y plus 9 doesn't factor. So we would need to do something like quadratic formula. And we don't got time for that today. So we would need to solve that in some other way to get our domain restrictions, because it has to be our roots or our solutions or zeros, whatever word we need for that. And we don't got time for that today. Okay? So we're going to get time-wise. We're at 36. We got 3 minutes. So we will talk about what we're going to do next tomorrow. We're going to do multiplication and division and start playing with rational expressions in many, many ways. All right, so please make sure you turn in homework 1.3. That is due today. Homework 1.4 currently listed as due Wednesday. I reserve the right to change my mind, but currently due Wednesday. I will only ever push backwards.